So up until now, we have been only working with questions where we were at equilibrium already. But a lot of the time, we throw some reactants into a vessel and the system eventually comes to an equilibrium, yes? And so for these problems, we're going to have to look at the shifts, okay? So we won't get to equilibrium until we have shifted. So the system will shift until an equilibrium is reached. And we still need to keep in mind, just like we did on our diagrams, that the shifts are proportional to the coefficients. Okay, so nothing has changed there. Okay, so here is a system where we start with reactants only. And you'll notice that we get to some final concentrations, yes? We could also start with just products. But what I want you to look at for these things is that the SO3, the products, end up at the same concentration. The SO2 ends up at the same concentration. The O2 ends up at the same concentration. So the equilibrium concentration of products over reactants will be the same. So it's the same regardless of how we start out. And that is the whole purpose. That is the whole reason it is called a K, because it is constant. It is constant no matter how you start. You will end up with the ratio always being equal to the value of KEQ. Okay? So in our little question coming up here, we have some NOCl and giving NO and Cl2. There is our reaction there. We place 2 moles of NOCl in a 1 liter flask at 462 degrees Celsius, and it is left to reach equilibrium shown above. When the equilibrium is established, so now we have some other information. When equilibrium was established, we had 0.66 moles of NO were present, and we're going to calculate our KEQ. Now, the only reason for giving the temperature is that we are being told the temperature so that we know it is at a constant temperature. Okay, and we are going to use this beautiful tool that you will be using for almost all the units from now until the end of the year, and it is called a rice table. I used to call it an ice table, but then I added the R because someone suggested then they could remember to write the reaction at the beginning. I liked ice table because I was like, use them, they're cool. But that's okay. Rice is cool too. Rice is good. So what you do is you write your reaction. Okay. And then you make 3 more lines in this table. You have an initial concentration, a change in concentration, and the equilibrium concentration. Okay. And I'm actually going to draw in some lines. If you would like a ruler, please let me know. I can grab you a ruler, but we'll just put those there. Then this just becomes like a little, let's plug things in from the question and then solve the little puzzle box. It's almost like, you know, one of those Sudokus or whatever where you fill in the things based on what else you have. So we have initially, ooh, look, initially. So 2 moles of NaCl in a 1 liter flask. What concentration is that? 2 moles in a 1 liter flask. 2 molar, okay? And that is, so our concentration of NaCl initial is 2.00 molar. So we can toss that into our rice table. 2.00. You are welcome to put molar there, but remember we're going to be working with Keq, and Keq has no units, so we can also just leave the units out here. As long as you remember that this always has to be moles per liter, okay? You cannot use moles in a rice table. You cannot use grams in a rice table. It has to be moles per liter. All right. How much NO and Cl2 do we have at the very beginning? None, because it says we placed some NaCl into a container. How much of the other things did we place into the container? Nothing. If we don't say it, there's nothing. Do we know any other pieces of information? Well, we're told when equilibrium is established, we have 0.66 moles of NO. So that's 0.66 moles in what volume? Still 1 liter. So that's going to be 0.66. And now, can we figure out anything else? You can figure out the change in the concentration of NO because we start at 0 and we finish at 0.66. So that has to have gone up by how much? 0.66. And as soon as you know one of the changes, you know all the changes because they just go as the stoichiometry of the reaction. You remember your x's and your 2x's and your 3x's. Okay, so 0.66 is 2x. So the change in Cl2, because it's just got a 1 in front of it, that's going to be, oh, by the way, is Cl2 going to go up or down? It's going to go up because if we are making one product, we also must be making the other product, right? We cannot make one product without the other product coming out at the same time. Yes? Plus how much? 0.33. Okay. Now, our NaCl, are we making it or are we using it up? Using it up because it is on the reactant side. So that's going to go down, and it's also got a coefficient of 2, so it's going to go down by 0.66. And now we have 2 minus 0.66 is 1.34. And this 0 plus 0.33 is 0.33. What would we do to solve the rest of the question? It asks us to solve for Keq, calculate the value of Keq. What would we do next? Yeah, we would use those equilibrium concentrations in what? The Keq formula. So before you put the concentrations in, you must write the Keq expression. Okay, so write the formula first. Keq equals Is that what you guys got? 0.080. Do you need glasses, Samantha? A little bit? Do you have some? Yeah? Maybe start bringing them. I'm just looking at you at the back there, squinting away. I've been there. I've done that. Okay. The Rice table is the accepted method of showing work for any question that deals with both initial and equilibrium concentration. Writing the Rice table is worth 1 to 2 marks, and these questions are usually worth maybe between 3 and 4 marks. So you can imagine this is like close to 50% of your marks for writing the Rice table and filling it in correctly. So you can lose up to half the marks if you don't show a Rice table. All right, now in the last question, we were told initially this was put into a flask. So we're like, oh, we're not at equilibrium yet. In this particular question, I'd like you to read it. And then we're going to see how do we know we're not yet at equilibrium, and we're going to need to use a Rice table. Take a read through that question. How do we know? How do I know that this system is not at equilibrium already and I don't just do, the calculations I did yesterday? Yeah? Yeah, it's allowed to come to equilibrium. That means we are not yet at equilibrium. So you can look for language like that. You can also say, we placed how many things into the flask? How many things? One thing. Placed in the flask. If you have one thing in the flask, are you going to be at equilibrium? No. Okay? If I had started with just I2 and Cl2, then there would be only 2 things, and those would both be products, and I can't be at equilibrium if I don't have some reactants present as well. Okay, so lots of clues. Be sure that when we get past, separating out the categories, we're at equilibrium. We're not yet at equilibrium. When you're doing like a mixture of the problems, you're looking for the language that tells you, is this a simple chuck them into KEQ or is this a rice table situation? Okay, you guys are going to fill in the rice table with the initial and equilibrium concentrations from the problem. You may need to calculate some of the moles per liter. Did I do it right so far? Yeah? What else am I going to need in order to solve things? I also know two other things in this chart without doing any math yet. What else do I know? Yes. I know the initial concentrations of the products because I didn't put any in. And at this point, now you should be able to fill in all of the changes. How we doing? We're good? Okay, guess what we're going to do next? We're going to be given a KEQ and asked to find an equilibrium concentration of something. At least I think that's what's happening next. Let's go take a look. What's on our next page? Oh, these are just little notes. Anytime you are given only reactants or only products, you know that the system is not yet at equilibrium and therefore you need to use rice. Anytime you see the words allowed to come to equilibrium or allowed to react, you know you are not at equilibrium. And so you need to use a Rice table. And anytime a system is not at equilibrium, you need to use a Rice table. Okay. Yep, I was right. We place some 2 moles of N2 and 2 moles of O2 into a 2-liter flask. And this is allowed to come to equilibrium. Oh my gosh, look, allowed to come to equilibrium. What will we be using? Rice table. Okay. What is the equilibrium concentration of NO? All right. Do you know where to start? You're going to start drawing a Rice table, absolutely. I would recommend when you are drawing Rice tables, it is not entirely necessary that you show the states. However, if you don't show the states, the chances of you including a liquid or a solid in your KEQ are greater because you won't notice them. Yeah? So it's a really good idea to put the states in your Rice table. And the easiest way to show Rice is to put these square brackets around I, C, and E. It is not entirely necessary for you to draw the lines. That is up to you whether you find them helpful or not. If you had a calculation that was more complicated than 2 moles in 2 liters, I would probably want you to show the calculation for how you get the concentration. But because 2 moles in 2 liters is so simple, I can probably be like, that's okay. That's 1 molar. Uh-oh. What do we do now? There's no things. Oh gosh. So we have a different unknown than KEQ. You're going to use X for the change. Okay? So anytime you have a coefficient of 1, these guys, do the reactants go down or up? The reactants go down, so those are going to have negative signs. The products go up because we're shifting that way. And anytime you have a coefficient of 1, just call it X. Anytime you have a coefficient of 2, call the change 2X. And then we are going to have 1 minus X. Don't forget to keep your sig figs in there. After your Rice table comes your KEQ expression. Oh, look what I did. What's wrong? You should not have a coefficient in the inside of your concentration brackets. I don't know why I did that. I've never done that in like years. That's okay. There we go. And I have to be honest, I usually don't solve this until I've chucked the numbers in. I usually chuck the numbers in and then solve, but you can do it the other way too if you want to. 4.51 times 10 to the minus 3. And one of the reasons I like to keep it in this format is that I look at this and I go, oh my God, that looks like a quadratic equation. Ooh, yucky, yucky, yucky. Except, is there a cheat? Is there a cheat so we don't have to do a quadratic? There is. What's the cheat so we don't have to do a quadratic? What? We just square root the whole thing, okay? All right. I want to see if you guys can do the algebra on this. Try the algebra on it, and then I'll show you. Yeah. I don't know. Why? Does it do algebra for you? Oh. Oh, I did wrong. Thank you. Oh, there we go. Okay. Let's fix this. 2.067. 72. I'm going to call it X. 2.067157. 0.325. 0.0325. Did I do that wrong? Wait. I may have done wrong. Wait, no. No, I think I did. Yeah. Is good? Yeah. Okay, so you should be able to do the algebra. I don't know. Let's look up AP Chem Desmos. Ooh. Can you use Desmos on AP Chem? No.
No.
Wait, Desmos is available as an option.
Hold on. Our Desmos calculators. Oh, hang on. What? Oh, yeah. In Blue Book for all, Desmos is available as an option in Blue Book for all test takers. This is AI. I don't always test AI. What is the, you know what? I'm going to have to ask AP exams calculator policy.
Use a calculator.
There are updates to the types of Desmos calculators available through Blue Book. Please note that the policies AP stats, built-in Desmos graphing, okay. Calculus, yada, 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 yada. Chemistry, built-in Desmos scientific or graphing calculator through Blue Book. Both types of calculators will be available. I would advise bringing your own just as a backup in case, but you know, yeah? Okay, there we go. Yeah, there is. Yeah.
Do we run it in this?
No, it's hard to get enough interest in a regular environmental science course to start with. So, all right, there are some exercises here. We're going to skip that and carry on. Which way will it shift? Oh, this is interesting. This is on page 100. Up until now, when we have been not at equilibrium, we've had only reactants or only products. But just because I give you some reactants and some products, does that guarantee that that's going to be an equilibrium mixture? No guarantee. So what we're going to have to do is we're going to have to decide, if I give you this mixture, are we at equilibrium already? Or do we need to shift to the left to get to equilibrium? Or do we need to shift to the right to get to equilibrium? So we are going to use this value, which we call Q, okay, which is also known as the K trial. So it's not at equilibrium. You're trying those values out in the KEQ expression, or it's called the trial KEQ. I prefer Q because it doesn't actually say K because Q is not a K, right? It's not a constant. It just depends on what concentrations you're given at the beginning, okay? So the reaction quotient Q for quotient, it is identical to KEQ, except instead of using equilibrium concentrations, you will be using initial concentrations. Okay, so for KEQ, for this system here, we're going to use our equilibrium concentrations. For Q, the expression is the same. The only thing different is we throw in the initial concentrations. Just so you are familiar with the terms, Q can also be called K trial or trial KEQ. You will come across those from time to time. Q is the Goldilocks of equilibrium. Okay, we've got too big, too small, and just right. Okay, so if Q is too big, so if Q is bigger than KEQ, then Q is too big. That means because Q and KEQ are the concentration of products to the concentration of reactants, that means that ratio is too big. And if that ratio is too big, do we want to shift right or left? We want to shift left because we want to shift away from products. We want to make the top number smaller and the bottom number bigger to make the entire ratio smaller. So we must shift to the left in order to produce more reactants. And we can put under here and use up products. Until the ratio of products to reactants equals Keq. If, on the other hand, Q is less than Keq, then Q is too small. Which means our ratio of products to reactants is too small. And therefore, the system has to shift to the right to produce more products and use up reactants. Until the ratio of products to reactants equals Keq. And if Keq is equal to Keq, then Q is just right. Do you guys know the story of Goldilocks? Anyone not know the story of Goldilocks? It's okay, because if you weren't raised here, right, you may not. It's okay. So there's this family of 3 bears, and they get their porridge, and it's too hot, and so they decide they're going to go for a walk while they wait for their porridge to cool. And they live in a cottage because that's what bears do, right? They live in a cottage. Anyway, so they go out for a walk to wait for their porridge to cool, and this little girl with golden hair comes along, and her name is Goldilocks, and she decides to stop into this little cottage, and she goes into the cottage and she looks around and she's like, oh, there's 3 chairs here. And so she goes and she sits in the one chair, and she's like, oh, this chair is too big. And she sits in the second chair, Mama Bear's or Baby Bear's chair, and she goes, oh, this chair is too small. And then she sits in Mama Bear's chair, and she's like, oh, this chair is just right. So she has a little relax there. And while she's relaxing, she starts thinking, oh gosh, I'm a little bit hungry. So she goes to, she smells a little something from the table, and she goes over to the table and she sees 3 bowls of porridge, which is kind of like oatmeal or congee. And she goes and she tries the first one. Oh, this porridge is too hot. And then she tries the next one. Oh, bleh, bleh, this porridge is too cold. And then she has the last one, and oh, this porridge is just right. And then she eats it all up. And then she gets tired because she's having like a carb, like crash. And so she I wonder if there's anywhere for me to lie down. So she goes upstairs and she finds 3 beds there, and she lies down on the first bed. Oh, this bed is too hard. Second bed, oh, this bed is too soft. Finally, she lies down on the 3rd bed, and that bed is just right. And then, so she's sleeping there. The bears come home, and then they say, oh my God, this is a long story. They say, who's been sitting in my chair? Who's been sitting in my chair? And then they say, oh, someone's been eating my porridge. Someone's been eating my porridge. And then someone says, oh, someone's been eating my porridge. And they ate it all up. Oh yeah, right. The chair that was just right. She broke that chair. Terrible girl. Breaks into a house, breaking chairs, eating porridge. Anyway, then they go upstairs and they're like, oh, someone's been sleeping in my bed. Oh, someone's been sleeping in my bed. someone isn't sleeping in my bed, and there she is. And then she runs off, and the bears chase her out of the house, and she never comes back because she was scared of the bears. There we go. So, too big, too small, just right is Goldilocks. I can't believe I spent that long telling that story, but there you are. So, if Q is just right, that means the initial products over reactants is just right, which means the system is already at equilibrium. Okay? So sometimes we will use this in conjunction with a race table, and sometimes we will just use it to predict which way the equilibrium shifts. So here's an example. This is just which way will the equilibrium shift. So you are starting with 4 molar, 2 molar, and 3 molar. And those are our initial concentrations. In which direction must the reaction progress to reach equilibrium? So you say, okay, I am going to write my Q expression. How do you write a Q expression? Exactly the same as a Keq expression. I would probably label them as I, just for completeness. So I do C2, H2 with an I, and then H2 with an I over CH4 squared with an I. Oh, and the H2 is cubed, right? So we would have 2 times 3 cubed over 4 squared and we get 3.375. So you get marks for writing the Q, writing this, plugging in your values, and getting this number. And then you will also get marks for saying Q, which is 3.375, is greater than Keq, which we are given in the question. It is 0.154. Okay, so Q is greater than Keq, and therefore, now, you can think this through. You can be like, I have too much products and I need to shift towards the reactants. I'm going to put that over here because you don't have to write that. Q is too big. So products over reactants is too big. Therefore, we need to shift away from the products towards reactants. That says towards, TWDS, towards reactants, which means we are shifting to the left. Now, in this next example, my feeling is that these numbers here, which are like 0.035, 0.5, 0.08, we got a 5-liter vessel. I would show the work for finding the concentrations, okay? I would say, okay, what is my concentration of SO2 initially? It is 0.035 moles in 5 liters, which is 7 times 10 to the negative 3. 7.0 times 10 to the negative 3. Concentration of SO2, Cl2, 0.500 moles in 5 liters equals 0.100 molar. I forgot my molar over here. And then we have to do Cl2. Cl2. Oh, and those are all initial. 0.080 moles in 5 liters. 0.016 molar. All right, so now we have our initial concentrations of everything. Can you guys figure out which way it's going to shift? Show finding concentrations. If you're dividing by like 1 liter, probably don't have to show it. If you're dividing by 2 liters, you might need to show it. I feel like these are weird enough numbers that you should probably show your calculations for this one. Did I do it right? Did you guys get the same numbers? What's that? 1.12 times 10 to the negative 3? Okay, now, just so you're aware, sig figs don't matter that much here because we're just being asked which direction it shifts. So whether you write 0.0011 or 0.00112 doesn't matter too much because we aren't asked for a numerical answer. We're asked which way does it shift.
Also, by the same way.
Huh? Why does it say a temperature? Just so that you know that that's the KEQ at 100 degrees, because KEQ changes with temperature. Okay? And once again, I like writing down my thought process for this. Q is too small. Products over reactants is too small. Therefore, we must shift to the right. I guess I should not put like that, because that looks like reactants, to make more products. How are we liking KEQ so far? Is good? Not too hard? Yeah. What's that? Yeah. I mean, you don't have to show this part here, right? You don't have to write that. I just like doing it for my own little brain, because my own little brain, if I don't write things down, tends to go backwards from how it should, because I write right and I mean left and all those things. So yeah. As you may have noticed. Okay. All right, and here we have a combo question. Initially, we put 0.5 moles of each reactant and 0.3 moles of each product into a 1 liter flask. When equilibrium is established, what is the concentration of SO2 if KEQ is 1.5 times 10 to the minus 2? How do we know that we need a, do we need a rice table for this question? Take a read through the question and let's decide, do we need a rice table? We've got an initially. We also have a when equilibrium is established. Okay, so this tells us that we will need to use a rice table. Okay, so we're going to use all of our tools here. How do we know that we're going to need to use a Q for this question? We have initial amounts of all things, both reactants and products. So I would start with Q, because then you know which way it shifts, and then when you start doing your rice table, you'll be able to put your pluses and minuses on the right side. Does that make sense? Okay, so let's start with Q. What tool are we going to take out of our toolkit next? We took Q out of our toolkit to figure out which way it's going to shift. What tool will we take out of our toolkit now? A rice table. Off you go. So I'm just going to interrupt you for a moment here and say that often people will get to this point and they won't have done a Q because they're like, okay, I'm going rice. And they get to here and they say, I have more reactants than products, therefore it must shift to the right. But it doesn't work because you need to look at what the actual position of the equilibrium is, right? The actual equilibrium has a small product over reactants, yeah? So you need a small amount of product over a larger amount of reactant because this is less than 1. So this favors the reactants. This particular equilibrium favors the reactants. Now, the question is then, is it favoring the reactants enough yet? Or is it favoring the reactants too much? Or is it not favoring the reactants enough yet? And that's what the Q is going to tell you. The Q says, I've got too much product. Because this value is too big, my product is too big. So I need to shift then to the left to use up that product. So we're going to put then our pluses over here and our minuses over here. Now, if you miss this, and you're like, I never did a Q, and let's say you put your negatives on the wrong side and your pluses on the wrong side, it will work. You'll just end up with a negative value for X, which is a little ugly. And I will tell you that your answer is inelegant, which is not a compliment. Okay? You should, with a question like this, figure out which side is positive and which side is negative. You are shifting to the left, therefore your plus signs are going to go here and your negative signs are going to go on the right-hand side. All right. Have fun doing clubs day. The rest of the lecture is recorded, so no worries. Okay, we're just, at this point, it just becomes throwing in some X's and doing some algebra like we did earlier, okay? And again, we're gonna have a square root, the whole thing, okay? So you missed nothing, okay? Don't worry. And now we go through and we put our products on the top, 0.30 minus x. We've got that twice, so that's going to be squared. And then on the bottom, we've got 0.50 plus x, and we've got that twice, so that's also going to be squared. 0.50 plus x squared. And hopefully somewhere back in our question, we were given a value for Keq, because if we weren't given a value for Keq, we cannot solve the question. But we were. It is 0.015. What? Did I get it wrong? Hang on. 1.5 times 10 to the minus 2, which is 0.015. Those are the same. Okay, I have a tendency when it's a small number like that and when I am doing algebra to write it like this because it makes my writing numbers less complicated. Okay, so I have 0.015 times 0.5, which is 7.5 times 10 to the minus 3 plus 0.015x. Oh, no, I did that wrong. Bad. Wrong. What did I forget to do? Square root. There we go. Let's try that. I've done a bad thing here. I got to the end and I just put a box around that. And I'm like, hang on. Did I actually answer what the question was asking me for? No, I need to go back and I need to say, what was the question asking me for? Question asked me for the equilibrium concentration of SO2. And that is 0.30 minus x. And we get 0.087. Yeah. And now I'm going to ask you, excuse me, about sig figs. Are my sig figs correct? my lovely 9 students that are left. What's the rule for subtraction? Of the one, we go to our first uncertain digit. What is our uncertain digit in 0.30? The 0. And in the 0.2127, that came from a bunch of numbers which had 2 sig figs, right? So this was all multiplication and division and nonsense and whatever. So this should have 2 sig figs here. So our uncertain digit is in the hundredths position, the second decimal place. So that's our uncertain digit. So this would then have to round to 0.09. And because it is a concentration, that would be molar. And I'm really regretting having squashed this down at the end of the page so much, but that is our final answer, is 0.09 molar. Did you? What did you get?
It's slightly, I think, because I want 0.
Oh, did I write 2127 and it should have been 2721? Okay. Let's try it again. 0.23876 divided by 1.1225. Okay, 2127. Okay, so I still get that. Let's see if there was an error back here somewhere. 0.015 square root. Okay, and then times 0.5 equals 6124. Is it possible you switched your 27 and your 21? Let me see. Let's look. Okay. Well, okay, so you got the same number down. That's right. Yeah. Did I add again? And I should have subtracted. Point 0.3 minus 0.6124. That should be 0.238. Oh, okay, yeah. There you go. We figured it out. We're good. Alrighty, and that takes us to the end of this. So for homework, what we can do is we can, let's see, how many questions are on here? 3. Oh, there's 4 here. And then there's 1, 2, 3 here. You guys can do 7 questions over the weekend, right? Yeah. What? Well, there's 4 in 2.3, so there's 4 on page 99. So you're going to do page 99, and you're going to do page 103. Page 99 and 103. Okie dokie. And I don't think it makes any sense to really go any further today. What is like the last one? Yeah, no, we can do that next day. It would really make sense to have this quiz on Tuesday or Wednesday. Wednesday's better. Sure. Let's have the quiz for KEQ Math on Wednesday. All right. And it would make good sense to have the test on Friday, but I don't think that's going to work. So what we're going to do is we're going to have our quiz on 2.3 and 2.4. Oh, I forgot we got to do 2.4 as well. 2.3, 2.4 on Wednesday. And then we'll have our tests the following week on the next Wednesday. So what do we got here? I can get rid of September. Now it's October. So this is on, the quiz is on Wednesday, October 8th. And then the test is on Wednesday, October 15th. Okay, and we might start, and we'll definitely do some AP stuff in between there, and maybe even start on our next unit. We'll see. Okay? But I think that gives you the best amount of time, considering that you have a, I don't know, whole bunch of people have 2 tests on Thursday, next Thursday. So I think that gives you a little gap in between. So gives me time to mark your quiz, get it back to you, study over the long weekend. Have you seen all the writing on these things? No, I also decided yesterday, I was like, I didn't go for a walk the day before or do any sort of exercise the day before. So I was like, I gotta go for a walk because I can't like let my body fall apart just because it's October like I do every year.
There's a lot of writing.
There's a lot of writing. So I'm just gonna keep chugging away on it. I'll get there. Turn the hot plate off and maybe unplug it, but just leave it where it is because it'll still be warm. There we go. Yeah. We'll let the next class decide if they want to use it.